Good afternoon everyone. So welcome back to laser technology session. So in the last class we have discussed about the broadening mechanisms such as collision broadening. So we discussed in the collision broadening mostly happens in the gaseous molecules. So where you have a radiating atom, so when there is a collision between the two atoms, you have a lot of sudden phase change appears. This sudden phase change is resulting your radiation frequency is changing, so that is broadening your your line widths. So that is mainly your, when there is a collision there is a perturbation to the energy levels, so that means there is a shift in the energy level resulting the your transition frequency is changing. So then we measure the line widths, so using your collision time as well as the TC, the time between two collisions. So from this we figured out that in general or practical materials or the practical systems, your collision time is much shorter, is almost instantaneous compared to your TC, that is your time between collisions. So the time between collisions depends upon the mean free path, so that is approximately in the microsecond time scales. So whereas your collision time scales will be in the sub-picosecond time scales. So this time scale difference is order of magnitudes. Okay, so then we figured out that your delta TC is much less than the TC. So your TC is very short, your delta TC is very short at the collision time, because that is almost, you can see it's very instantaneous. So during this time you have a change in the frequency. So not only change the change in the frequency is also gives you the change in the phase. So now if you see, this is the radiation frequency from the emitting atom. So now at this instant of time your phase is completely changes because of your radiation is different frequency. So now during this time, this window of the time, you have different frequency comes from the atom. Okay, so now again until the next collision you have the same frequency is maintained, so that phase is same. So from there we estimated the line width of this broadening mechanism. So the collision broadening, so we get, this is from your the total collision times. You have to take the probability function, that is from the kinetic theory. So then you will get the normalized line shape function like this. The expression will be 2 by tau naught 1 by 1 plus tau naught square omega minus omega naught whole square. So the full width of maximum for this distribution is 2 by tau naught, and this expression also follows the same Lorentzian function. So now the distribution from your natural line width as well as the collision broadening gives you Lorentzian distribution. So now if the system has, in general you always have a natural broadening that is added by the whatever the other broadening mechanisms. So inherently we always have a natural line broadening for the atoms. So now what are the other broadenings will add up to the expand the width of your spectral region. Okay, so your delta omega is your width of the spectrum, or a line width of your is a line width, you can call a natural line width plus the collision broadening line width. If any other broadenings will be there, then it will keep on adding, gives you the broadened spectrum. So far about the collision broadening. So now we will move on towards the Doppler broadening. So when now we consider the atoms also moving. When these atoms are moving, they are interacting with the electromagnetic radiation. So now what we can see the difference is the apparent frequency of the wave is different from of the stationary atom. we can consider an example when this is a stationary atom. Now it is radiating in all directions. In all directions you see the wavelengths or the frequency is the same. Now for example, if the atom is moving, so this is the initial position and this is the final position. Now you see in this direction, for example, observer is here, he can, these frequencies are shorter, and if observer this side, he can hear the frequencies are longer. So now the apparent frequency is different. So this is called a Doppler effect, and due to this the broadening comes into the picture. This broadening is called Doppler broadening. Okay, so this is very simple. Like you have a stationary, for example, this will work even for the sound waves. Now for example, if you drop a stone in a pond, we know the pond is very in the rest motion. There is no disturbance in the land before you create the disturbance. Now you see the disturbance is concentric, like a concentric circle. So you can see the disturbance will propagate in all directions. Okay, so now if you see in the other direction, along the g direction, the disturbance is also moving. So then if the observer from the bottom, he feels the different frequencies. Okay, so now the same thing happens when you hear when the train is going away from you or it's coming for you, the sound frequency you can observe the frequency change. So this effect you call a Doppler effect. The same thing you can for the light waves also, the same thing will happen. Because of this movement of the particle or the atoms here in our case, because of the movement, the apparent frequency will be different. So this is called Doppler broadening. Now you see the radiating frequencies will be in different directions, will be different because the particles are also moving. Now if you take any other directions, you always see the radiation frequency in whichever the direction you will take, it always will be different. Okay, so now if the radiation is assumed to propagating along g direction, so the apparent frequency by the atom which is in the g direction, now it is your g direction has certain velocity associated with it. So now this velocity has to be, your apparent frequency will be depending upon this factor. Your W prime is equals to W naught by 1 minus Vz by C, where Vz is the velocity in the g direction. So I am assuming my radiation propagating along g direction. So now I am neglecting the higher order terms. So you can take this one to the numerator side. So you will get 1 minus Vz by C power minus 1. So I am neglecting the higher order terms, as your velocity of Vz, higher order terms will be very negligible. So I will get the first order term omega prime equals to omega naught 1 plus Vz by Vc. This is a simple expansion of 1 minus x whole power minus 1. So neglecting the higher order terms, your frequency will be modified like this. Okay, so now your Vz is not comparable to the light velocity. So if it is comparable to light velocity, you have to apply the Einstein relativistic dynamics. So in principle, your V of Z is much less than the light velocity. So this effect of the motion is changing the resonant frequency of the atom. So because of this, your velocity component in the denominator, so that is actually changing your resonant frequency of the atom. So now you solve the equations, so you will get the distribution function like this. So your g of omega, your Lenz's function is c by omega naught m by 2 pi kbt whole power 1 by 2 e power minus mc square by 2 pi kbt omega minus omega naught whole square omega naught square. So I will leave this expression up to you to solve it from this. And now you see this is always constant. So now your expression is in terms of u for minus kind of a minus x square. These are some of the constants. Your omega is also constant. So now your omega minus omega naught square. So your g of omega is depending on the frequency. So your parameter, changing parameter or variable is omega. So now if you see this expression in the form of g of omega equals to e power minus omega square. So I'm remaining everything is almost, these are all factors are constant. Your omega naught also a constant because it's a resonant frequency, or you can call a central frequency. So now your g of omega is proportional to e power minus omega square. So what is the distribution? E power minus x square. So if you plot the e power minus x square, this will be your Gaussian distribution, right? So this is your Gaussian distribution. Now the line shape function of the Doppler broadening follows the Gaussian distribution. Okay, so because these are all constants, these will only play whether the intensity is higher or lower. These all constants will support to increase the intensity or decrease the intensity, but the spectral lines, whatever you see, the spectral lines will be depending upon only this function. So that is this factor. Okay, so that factor only decides what are the spectral lines in this distribution. So this is our Gaussian distribution. This Doppler broadening always gives you the Gaussian distribution. So as we discussed about several times, the Gaussian beam, even we discussed when the laser characteristics, the divergence of the Gaussian beams. So now your Gaussian beam is actually a transverse amplitude. So you have an electric field in the beam. So your fundamental mode of your many practical lasers, the fundamental mode is your TM00 mode, right? So now the amplitude of this distribution in a transverse direction, that is follows a Gaussian. If you take any radial distance, if you from the center you go along any direction. So now you can see the Gaussian beam in 3 dimension, right? Whatever I am showing here is a 2D plane, but you assume a 3D plane, or in 3D, in the 3D you go any direction, like you assume a sphere. So when you have a sphere, from the center you go any direction, it follows your Gaussian distribution. Like for example, so I can show you from the taking such a way that like make a 3D picture, but assume this is a sphere. Okay, so now from this body center you make one end to other end. If you take any cross sectional view, or this end to this end, if you propagate, the intensity distribution always have a Gaussian distribution. This is for you to show you the 3D picture, but in principle you have to imagine a sphere. In the sphere, from the one end to other end, it has to pass through the center of your sphere. Take any axis, you will get this distribution. So your amplitude or your intensity follows the Gaussian distribution. Okay, it has a width of delta omega, that is your full width of maximum.